So I can start?
Not just yet, sorry. Should say somewhere that is. Okay. Great. So we are very glad to start our APRG seminar this year with Peter Šemrl from Ljubljana, and he will talk about Wigner's theorem. Over to you, Peter.
Thank you very much. So I will speak on Wigner's theorem, quite important, I mean, very important. One of the cornerstone theorem, the basic theorems in the mathematical foundations of quantum mechanics. I will speak just a little bit about this background in mathematical physics, but I do not really understand the background in mathematical physics. I will speak about the mathematical problems. I just know there is some background there, but please don't ask me questions too much about the background because I do not really understand it. So H will be a Hilbert space, and then by P and H, I will denote the set of projections of rank N, which means projection. This means self-adjoint bounded idempotent, which means that you have image and kernel and they're orthogonal. So if it is of rank N, means that the image is n-dimensional. And of course, because the kernel is orthogonal complement, so the projection of rank N can be identified with its image. So actually, we can speak either of projections of rank N, the set of all projections of rank N, or we can speak of the Grassmann space of all subspaces of dimension N. So we have the Grassmann space of all the Grassmann set, the Grassmannian of all subspaces of dimension N. How do we introduce the distance into this Grassmann space? Simply because we can identify these subspaces with corresponding projections. Projections are bounded linear operators. We have the usual operator norm, and then we can measure the distance. That's just the usual way. Now, in quantum physics, projections of rank 1 represent pure states of a quantum system. And if you have two projections of rank 1, then you can calculate trace of the product, and that's the transition probability between those two pure states. Wigner's theorem, this is really basic theorem. I mean, you start with one of the starting statements in the mathematical foundations of quantum mechanics is the description of symmetries. So you ask how you can change the quantum system without affecting these transition probabilities. And of course, what you can do with the pure states, you can just turn them around with a unitary operator. Or there is one more possibility with anti-unitary operator. What is anti-unitary operator? Is like unitary, just it is not linear, it is conjugate linear, but everything the rest is the same. It's bijective, it's isometry, but it is not linear, it is conjugate linear. So it does not preserve inner product, it just turns it around. And so what is now this Wigner's theorem, which is actually very simple. We have a Hilbert space, we have a symmetry. So symmetry is this bijective map on pure states. And this bijective map preserves transition probability. If you have such a map, it is necessary a unitary similarity or anti-unitary similarity. So we just turn around by unitary or the system by unitary or anti-unitary operator, and such maps will be called standard maps. Now, if we have projections of rank 1, so two projections of rank 1 are involved here. If you have two projections of rank 1, then actually everything is happening on a two-dimensional subspace. You take those two, you take the image of the first one, the image of the second one, the linear span, the orthogonal complement is a subset of the kernel of P as well as the kernel of Q. So everything is happening in 2 by 2 matrices. And then it is an easy exercise how you measure this transition probability. Okay, this is trace PQ. It depends on the norm of P minus Q, or if you prefer to think geometrically, it depends on the angle between the images. images are one-dimensional subspaces, and you can define in a natural way the angle between them. And of course, you have formulas which connect trace of the product with the norm of the difference, I mean the distance between P and Q. And of course, there is a formula which relates this to the angle between P and Q. So, for example, if you have two projections of rank 1, then this is an elementary exercise that the norm of P minus Q is just the square root of 1 minus trace of the product. So, preserving transition probability is actually the same as preserving the distance. So, you can reformulate the theorem, that's all easy. Wigner's theorem, you now consider bijective maps on projections of rank 1 that are isometries, and such maps have to be standard. It's just a reformulation, nothing new. Now we have this theorem, and we are going to ask, can we do it a little bit better? What would be a little bit better? Do we really need bijectivity assumption here? The next question, here all transition probabilities are preserved. What if we preserve, for example, just transition probability 0? Trace PQ is 0 if and only if the product PQ is 0. So it is, can we describe all the maps that preserve orthogonality? Or perhaps can we describe all the maps that preserve not all transition probability, but just a certain fixed transition probability? If we go on with this formulation, then here we can consider, instead of projections of rank 1, we can consider, say, projections of rank 7. Can we prove anything similar on the Grassmann space of Grassmann space of all subspaces of dimension 7 instead of Grassmann space of all subspaces of dimension 1? These are all open questions that I will address in my talk. So do we need bijectivity? What if we preserve only orthogonality or any other fixed transition probability? Can we do this a little bit better, and can we replace projections of rank 1 with projections of some fixed rank? Say rank 7 or rank 12, can we do, say, something similar? Bijectivity, that's easy, known for a long time. So here we have exactly, so here we have, here we have more or less, it's almost the same as Wigner's theorem. There is one difference. In Wigner's theorem, it was a bijectivity here. Here we have the same theorem, but no bijectivity. We just have a map preserving transition probability, and it has to be standard. Now, in Wigner's theorem, this U was unitary or anti-unitary. Now we do not have bijectivity, so there is no need that this U is unitary, that this U is bijective. So U is in, if we drop the bijectivity assumption here, the conclusion is that the map is of the same form, but this U is not bijective, linear or antilinear isometry, just linear or antilinear isometry, can be non-surjective. This has been known for a long time, and if you want to have a very, I believe this is the shortest proof, self-contained, very simple, you can find it, it's by Georgi Gecher, you can find it in Physics Letters A. It was published in 2014. Now, the next question is preserving just one transition probability. We start with transition probability 0, and we have, again, an old theorem by Ullhorn. So what we have, as before, we have the set of all projections of rank 1, or if you prefer, the set of all one-dimensional subspaces, or if you prefer, the projective space over a Hilbert space H. We have a bijective map, and this time just orthogonality is preserved. P and Q are orthogonal if and only if the images are orthogonal, and again we have the same conclusion. Now here bijectivity assumption is essential. Without bijectivity assumption, you can do crazy things, but I have no time to go into details. What if we preserve a certain fixed transition probability? So again, we have a map which is bijective, but now we do not have, like in Wigner's theorem, we do not have the assumption that transition probability of phi p phi q is equal to transition probability pq. No, we have just a fixed transition probability, and this fixed transition probability is preserved. Do we have the same conclusion? The answer is yes. It is enough to preserve just one transition probability, then all transition probabilities is preserved. All transition probabilities are preserved, and we have a standard symmetry. The study has been initiated by Chik Wong, Li, Lucian Plevnik, and myself quite some time ago, maybe some 10 years ago. And then a substantial step forward was made by Georgi Geher, and then Georgi Geher and Michia Mori together published the final solution. It appeared in International Mathematics. No, it will appear in International Mathematical Research Notices. So this is rather new result. I believe that electronic version has been already available on the webpage of IMRN. If not, you can find the paper on archive. Now, what do we have here? This is Ullhorn's theorem. We have a bijective map, and orthogonality is preserved in both directions, and then the conclusion is that the map is of standard form. Can we do any better? Can we do any better? No, bijectivity is essential. But without bijectivity, you can do counterexamples, but crazy counterexamples, but to make them, you have to go to the infinite dimensional case. What happens in the finite dimensional case? Can you do better in the finite dimensional case? What would be better without bijectivity? Here we have preserving orthogonality in both directions. Can we assume that orthogonality is preserved in one direction only? Yes, all this is true. And this was, as far as I knew, till very recently, this was a new result. I read this result in the paper of Pankow and Fitterlein. It will appear in Bulletin of London Math Society. So what is the result? We have a finite dimensional Hilbert space. Okay, we have a technical detail. I'm speaking about the main idea, so I will not mention all. They're written here, but I will not mention those technical details. It is rather clear why it is needed. Two-dimensional case is trivial, but let's forget about those things. So what we have a map on projections of rank 1, no bijectivity, nothing, and orthogonality is preserved, but in one direction only. Still, we get the same conclusion. But then very, very recently, I discovered that this result has been actually proved 10 years ago. But it was why I was not aware of this result. Actually, it was a lemma for some other result. In my personal opinion, this lemma is much more important than the general result that was proved in this theorem, because this lemma is now really optimal version of Wigner's theorem in the finite dimensional case, because we have the weakest possible assumption. Wigner's theorem again is bijectivity and preserving all transition probability. Here we have no regularity assumption like bijectivity, and just zero transition probability is preserved, and this transition probability is preserved in one direction only, and we already get the same conclusion. So this is the optimal version in the finite dimensional case. So I will present here a very, very short proof of this statement. It was published in my paper that appeared last year in Journal of Physics A, and this short proof is based on Gleason's theorem. Gleason's theorem is another theorem in mathematical physics that is of basic importance. Now, if we go back to Wigner's theorem, Wigner's theorem, which is written here, is is of fundamental importance, but actually it's a very easy theorem from a mathematical point of view, because if you take such a map if you take a bijective, here we have not Wigner's theorem, we have a stronger theorem, Ullhorn's theorem. So we have a bijective map on projections of rank 1, on one-dimensional subspaces. So we have a bijective map on the projective space over Hilbert space. And if orthogonality is preserved, then it's very easy to see that this map satisfies all the conditions of the fundamental theorem of projective geometry. So you just apply the fundamental theorem of projective geometry, and then you have a little bit of technical work, maybe 5 or 6 lines, and you are done. So while Wigner's theorem is very important in mathematical physics, but from a mathematical point of view, it's almost trivial once you know fundamental theorem of projective geometry. Gleason's theorem maybe is, again, a very important theorem in mathematical physics, maybe not as important as Wigner's theorem, but mathematically it is much, much deeper result, much more non-trivial. So what is Gleason's theorem? It's another theorem about certain things on pure states, on projections of rank 1. If I have projections of rank 1, I have finite set or infinite set in the infinite dimensional case. I will call such a set complete orthonormal system of projections of rank 1, COSP, complete orthonormal system of projections of rank 1, if any two are orthogonal and I have a maximal such subset. Means that there is no other rank 1 projection that is orthogonal to each of them. So I mean, it's clear what I mean by COSP. If I take such a complete orthonormal system and I take a unit vector in the image of Q1, then a unit vector in the image of Q2, and so on, I get a complete orthonormal basis. I get an orthonormal basis. That's COSP. So it's easy to understand what this is. What is a density operator? Density operator is positive operator, means that it's self-adjoint and the spectrum belongs to the set of non-negative real numbers, and is a trace operator, and its trace equals 1. Now what is Gleason's, I will call it Gleason's function. It's a function defined on the set of all projections of rank 1. The values are in the unit interval. It's like some sort of probability function. And it has this property that for every COSP, I calculate this, the value of this function on each element. I sum up, and what I get is probability. Let me call this probability 1. It is some sort of probability, because if I have such Gleason's function, and if I take any projection, say a projection of rank 3, this projection of rank 3 is a sum of 3 projections of rank 1, and then in a natural way I can extend phi to this projection of rank 3. I just, if Q is Q1 plus Q2 plus Q3, I just take phi of Q1, phi of Q2, phi of Q3, I sum up, and I get the value of phi Q, and this is well-defined function, and it behaves like a measure. If I have 2 projections P and Q and they're orthogonal, then phi P plus phi Q is going to be equal as phi of P plus Q. It behaves like a probability, some sort of, we have orthogonal additivity, and we don't have just additivity, we have actually countable additivity. What are examples of such Gleason's functions? If you take a density operator, and then if for each projection of rank 1 Q, you calculate trace dq, this is a trace operator. So this is, I mean, no, this is well defined anyway for any operator because Q is of rank 1. So you calculate this trace. What you get is exactly Gleason function. It satisfies this property. What is Gleason's theorem? That all Gleason's functions are of this form. All Gleason's functions are induced by some density operator. And this is rather non-trivial theorem. I mean, the proof is, once again, not that complicated, but I mean, it was, there are clever tricks that Gleason's had to invent to prove it. Now, okay, I have here this optimal version of Wigner's, or if you want, the optimal version of Ullhorn's theorem. I have finite dimensional space. I have a map on projections of rank 1 that preserves orthogonality in one direction only. And I want to conclude that this map is of a nice form, that it is a standard map. How I do this? Using Gleason's theorem. So I have this map phi. I take a density operator, and then I define this function phi sub d. Phi sub d on a projection of rank p. I just calculate trace d times phi p. Now, phi preserves orthogonality. Assume that H is, say, 7-dimensional. What is then cosp? Cosp is, you take any 7 projections of rank 1 that are orthogonal. This is going to be a complete system of orthogonal projections. Because orthogonality is preserved, it is mapped into 7 orthogonal projections of rank 1, and because dimension of H is 7, of course, if you have 7 orthogonal projections of rank 1, they form a complete orthonormal system of projections of rank 1. So my map phi send every cosp to cosp. So this is a Gleason's function. And so a Gleason theorem can be applied. So this Gleason's function is induced by some density operator E. So trace d phi p is equal to trace EP. Of course, this E is a density operator, and of course, it depends on D. Now for every D, I can find such a density operator E. I will take d phi q, where q is any projection of rank 1. I choose it and then I fix it. Of course, q is a projection of rank 1, so phi q is a projection of rank 1, so phi q is a density operator. I plug it in and I get trace phi q, phi p is equal to trace EP E sub q, where this is some density operator. Now, I do not know at the moment what is this density operator. I just know that this equation is satisfied for all projections of rank 1. But now I plug in q. For p, I choose q. What I get? I get here trace phi q, because this is a projection of rank 1, this has to be 1. So trace a sub q times q has to be 1. But this is a density operator. And if I want to get the value 1, the only possibility is that E sub q is equal to q. This E sub q has to be q. So what do I get? I get this equation. Now, this holds true for every P projection of rank 1. This is, I have chosen q in an arbitrary way. So this is true for all projections q of rank 1, all projections p of rank 1, so transition probability is preserved, and we are in the same situation as in Wigner's theorem, and then we apply, for example, Geher's short proof, and we are done. So the optimal version of Wigner's theorem comes immediately from Gleason's theorem. I mean, for me, it was kind of, when I found this short proof, was kind of satisfaction, because Gleason's theorem is deep, is some very deep theorem on projections of rank 1. Wigner's theorem is important, but it's easy, and it's somehow now we have this feeling that Gleason's theorem is really stronger because we get Wigner's theorem, not just Wigner's theorem, the optimal version, almost for free from the Gleason's theorem. Now this is another open problem. I mean, it's not open anymore, but another natural problem connected with Gleason's, with Wigner's theorem. So what was Wigner's theorem? One of the possible reformulation, you have a bijective map on projections of rank 1 that is isometry. The conclusion, such a map is standard. So bijective isometries on rank 1 projections are standard. What if we have bijective isometries on projections of rank 7 or any other fixed rank? We get the same conclusion, or almost the same conclusion. So this is a result. We have a Hilbert space. We have a bijective map on this. I mean, we have a fixed positive integer n. We have a bijective isometry on the set of all projections of rank n. And the conclusion is that this map has to be of a standard form. This is the conclusion, not exactly. If dimension of H is equal to 2 times n, then of course, say if you have 5-dimensional subspaces in 10-dimensional space, then you can send every subspace of dimension 5 into its orthogonal complement. This is still going to be isometry. Or if you want, you send every projection into identity minus p. This is still going to be isometry, and of course bijective isometry. But of course, this possibility appears only if the dimension of H is just the double of the dimension of subspaces that we are treating. So this was this theorem. This problem has been initiated by Botelho, Jamieson, and Molnar. The paper appeared in Journal of Functional Analysis probably some 10 years ago, and then the problem has been solved completely by Gecher and myself, and the paper was published again in Journal of Functional Analysis, I don't know, maybe some 3-4 years ago. Let me explain a little bit what is the idea and what was the main problem. If we go back to the case of projections of rank 1, so we are considering isometries. What is the distance between P and Q? What is the distance between one-dimensional subspaces? This distance can be expressed with the angle. These are projections of rank 1, so geometrically we are speaking of two lines, and this norm is determined by the angle between those two one-dimensional subspaces. The mutual position of two projections of rank 1 is determined by the angle between the corresponding subspaces. Now, what is the problem here? The problem here is that we have say, let's say that n equals 5. So we have 5-dimensional subspaces. If we have 5-dimensional subspaces, how we describe the mutual position of two 5-dimensional subspaces? If we want to describe this up to isometry, up to the unitary isometry, then we actually need 5 angles. These are so-called 5 principal angles. What we have here, the norm is preserved, and the fact that the norm is preserved means that just the largest principal angle is preserved. We have no idea what is going on with the other principal angles. So when n equals 1, the mutual position of subspaces is preserved, while here just the largest principal angle is preserved, and we have no ideas what happens with other principal angles. So this problem was much more difficult. And what was the idea of Georgi Gecher and myself? What we did, we took two projections. Say, let me speak of projections of rank n, but let me choose some concrete number. So assume we have two projections of rank 5, or if you prefer, we have two subspaces of dimension 5. We have two such projections, and then we take the set of midpoints. So what are midpoints? Midpoints are those projections of rank 5 that are the distance to P is at most 1 over square root of 2. And the same for the distance to Q. It is at most 1 over square root of 2. Now assume that those two projections of rank 5 are orthogonal. Then I just change the basis and I can represent them in this new basis, those two projections, like P is 1, 1, 1, 1, 1, 1, 1, and 0, 0, zeros, finitely many or infinitely many zeros, while Q is 5 zeros on the diagonal, then 5 ones on the diagonal, and then zeros all the way to the end. So these are, if you have two projections of rank 5 that are orthogonal, they have such a matrix representation, of course, in a certain basis. Now I want to see what are all those midpoints. And this is, with a little bit of work, not too difficult. I can show that the set of all midpoints is exactly the set of all such operators. Here we have 1/2 identity, 1/2 identity, and here we have 1/2 unitary operator, and here 1/2 U star, the inverse of U, where U is any unitary operator. In other words, the set of midpoints looks like the unitary group. I mean, it can be parameterized by a unitary group. Now, unitary group, we know that unitary group is a compact manifold. It has topological properties, a manifold. Of course, it's a compact manifold. I have a bijective isometry, so compact manifold is mapped onto compact manifold because all the distances are preserved. The topological structure is preserved. Now, what we succeeded to prove? We succeeded to prove that if we have two projections, and if the distance between those two projections is 1, then those two projections are orthogonal if and only if the set of midpoints is compact manifold. I have just shown that if P and Q are orthogonal, then this set is a compact manifold. So if they're orthogonal, midpoints look topologically like the unitary group, which is a compact manifold. If they are not orthogonal, then the manifold structure is somehow spoiled. This is technically complicated, but it can be shown. So now we have bijective isometry. Midpoints are mapped onto midpoints. Compact manifolds are mapped onto compact manifolds. Projections which are at distance 1 are mapped at the projections that are at distance 1. So if two projections are orthogonal, the images are also orthogonal. So in this particular case, when P and Q are orthogonal, not just the largest principal angle is preserved, all principal angles are preserved. And this is the first step in the proof, and actually is enough, because now we are in a similar situation like in Ullhorn theorem. Ullhorn's theorem was a bijective map on projections of rank 1 preserving orthogonality. Here we have now bijective map on projections of rank 5 preserving orthogonality. And what is the structure of such maps? Actually, I described such maps some 20 years ago. So here this result can be applied. That was the basic idea. But there were, I mean, it was difficult to prove. Actually, it was kind of difficult to prove that if P and Q are not orthogonal, that this manifold structure is spoiled. That was difficult. And of course, here are some technical assumptions. Dimension has to be larger than 2n. What happens if dimension is equal to 2n? That was particularly difficult. And we needed fundamental theorem of geometry of matrices, and so on and so on. But the main idea is here. When we had this idea, we somehow knew we are on a good way to the solution of the problem. If we look at this theorem, everything looks okay. So like nothing else to do. No, there is something else to do. What if H is infinite dimensional? Then we are not interested just in Grassmannians of, say, we are not interested just of Grassmannian of all projections of rank 5 or all projections of rank 17. Of course, the natural question is what happens with essentially infinite dimensional projections. So projections where both the image and kernel are infinite dimensional. Is there a similar result? The answer is yes. So if we have a separable infinite dimensional Hilbert space, we denote by P infinity the set of all projections whose images and kernels, both image and kernel, have to be infinite dimensional. Of course, if you take all those projections where kernels are finite dimensional, then you just consider orthogonal complements and you reduce this to the previous problem. But so this is the only remaining problem. What happens if we have the Grassmannian of essentially infinite dimensional projections? It essentially means that both image and kernel are infinite dimensional. And again, we have the same result. If we have a bijective map, of surjective, but of course, because of this property is bijective. If we have a surjective map on such projections that is isometry, then it has to be a nice map, a standard map. That was also proved by Georgi Gecher and myself, and it appeared recently in Advances in Mathematics. Okay, when I formulated the theorem, I made a mistake. I said it's a standard map. Okay, it's not just a standard map. It can be also, you can send every subspace or every projection into its orthogonal complement and then compose this with a standard map. Of course, this is again isometry. Can we use the same approach as with finite rank operators? No. What is the problem? The problem is that we have this second possibility, and this second possibility does not preserve orthogonality. Just look, if you have P and Q like this, these are, I mean, because H is infinite dimensional, you can make it, you can rewrite it as a direct sum of three equal copies. And then you take P, which is diagonal projection identity 0, 0 on diagonal, and Q 0 identity 0. What is I minus P is 0 identity identity. What is I minus Q is identity 0 identity. So we have in I minus P, you have identity here. In I minus Q, you have identity here. So these two are not orthogonal. P and Q are orthogonal, but these two are not orthogonal. So there is no hope that we will use the same approach. We have to do something. We had to do something different. What was the idea? This idea was slightly more complicated. But again, let P and Q be two orthogonal projections. Infinite dimensional projections. I mean, essentially infinite dimensional. The image is infinite dimensional, the kernel is infinite dimensional. And let us assume that P and Q are orthogonal. And then take a midpoint R. R is a midpoint, means that the distance to P as well as the distance to Q is equal to 1 over square root of 2. Of course, this is the minimal possible. I mean, if you want between P and Q to find R such that you minimize the distance to P and to Q, then this is the minimal possible distance. Of course, you have no straight lines in the set of projections. Now, if you have such situation, then you can construct a path such that the starting point is P. You start here, you end here, the end of the path is here, and exactly in the middle, you go through this path passes through the midpoint. So you start in P, you end your path in Q, and in the middle, exactly in the middle of the path is R, and you have these minimal distances between any 2 points on this path. Geometrically, this is a geodesic that starts with P, that ends in Q and goes through R. Just you cannot apply the usual tools from the differential geometry because you have no differential structure and things like that. Now, what is interesting, that what we have observed is that such a map exists, but there is exactly one. If you have this geodesic going from P to Q, this P and Q are orthogonal, and you make a geodesic, and you want to pass through this midpoint R, then you can do this in just one way. There are not many possibilities. And the same is true if you work with orthogonal complements. You just take orthogonal complements everywhere. How you do this? You take P and Q, which are orthogonal, so they have such a matrix representation. You forget about the last row and the last column. You somehow see those last row and last column, you can forget. Everything will happen in this upper 2 by 2 corner. So you have such, actually you have such a situation. P is such a simple projection. Q is like orthogonal complement. And for a midpoint without loss of generality, after turning around, you can take the usual midpoint between those two projections, 1/2, 1/2, 1/2. And then it is obvious what will be this path that will start here, that will go here, that will end here, and that will pass through this midpoint R. I mean, it's just easy to guess what is this path. And this is a unique path having this property. How to prove it? You have to deal with certain operator inequalities. It's possible. It's possible. What happens if P and Q are orthogonal and you have a midpoint? Then you have just one path with all these properties. If P and Q are not orthogonal, then you can construct more paths different paths going through the midpoint. And that's the trick. In such a way, you characterize orthogonality, but actually you do not characterize orthogonality. This happens, the uniqueness happens if and only if P and Q are orthogonal or their orthogonal complements are orthogonal, one or the other possibility. So what do you have? You have now a different situation. You have a bijective map with the property that P and Q, not before we had P and Q are orthogonal if and only if P and phi Q are orthogonal. Here we have P and Q are orthogonal if and only if what happens? Either phi P and phi Q are orthogonal or their orthogonal complements are orthogonal. So we have two possibilities. You have two projections that are orthogonal. You map them with phi. What will happen? The images will be orthogonal, or the orthogonal complements of the images will be orthogonal. And then what you do? You just prove, and that's not very difficult, that either you are in the first possibility all the time, or you are in the second possibility all the time. If you are in the second possibility all the time, you compose your map with the orthogonal complement, and you are in the first possibility all the time. So you have a map preserving orthogonality, and then again, bijective maps preserving orthogonality on these projections that are essentially infinite-dimensional. Such maps have been described by myself, I don't know, long ago, maybe some 20 years ago, and this is kind of a sketch of the proof of this theorem of Gleason and myself. So if I go back, we started with Wigner's theorem, and then we ask several natural questions. Do we need bijectivity? No. This has been known for a long time, and recently we have a very, very short, very simple self-contained proof. What if we do not preserve all transition probability, just one fixed transition probability? We still get the same conclusion. The result by Gleason and Mori. In particular, orthogonality. This is a classical result by Ullhorn. If we preserve just orthogonality, then in the finite-dimensional case, we really have the optimal version. We do not need any regularity condition like bijectivity, just preserving orthogonality and one direction only, and you get the result. Has been proved some 10 years ago as some lemma in some paper, has been reproved independently, has been proved by Pankow and Fitterlein, and I showed you that this actually follows from Gleason's theorem. And can we replace in Wigner's theorem rank 1 projections by rank n projections? Yes, and we get this more or less the same conclusion. Can we replace P1 by essentially infinite-dimensional projections? Yes, and we get essentially the same conclusion. Okay, there is one more possibility, that you map every projections first into its complement and then apply the standard map. And so all those questions are answered, and that's all I wanted to say. Thanks a lot for your attention.
Thank you. Exceptionally clear. Are there any questions? Yeah, go ahead. Go ahead.
Yeah. This is Raja. So is there something we cannot answer?
Sorry, Peter, I think both audio are on. One of audios or microphone.
Pardon?
If you have two screens you're logging, maybe one of them microphone and audio can be turned off. I think now my voice is not echoing. So yeah, Raja, go ahead.
I was just wondering if there's some interesting problem which still open.
I believe this is classical Ullhorns theorem. We have a bijective map which preserves orthogonality in both directions, and then it has to be of a standard form. Can I draw bijectivity assumption? No. And there are examples what you do. Simply you write H as a direct sum of two copies of H. On the first, so the map from P1H into P1H can be considered as a map from P1H into P1H plus H. And on the first summand, you just take the standard map and you play crazy games in the second copy of H. This is how you construct counterexamples. So bijectivity is needed here if you want to have a nice conclusion. Sorry. Bijectivity is needed, but as far as I know, this is open. If I have a bijective map and orthogonality is preserved in one direction, so you have implication just in this direction, I'm rather sure the conclusion has to be the same. So you have a bijective map from projections of rank 1 to projections of rank 1. The assumption is if PQ is equal 0, then phi P phi Q is equal 0. Just implication in one direction, not in both directions. I believe the conclusion is the same. It's so simple. You can tell the problem to any student after the very first basic course in functional analysis. You need almost nothing to understand it. But is it true or not? I have no idea. And I somehow I guess it's not even easy. It's elementary problem, simple to formulate, but I have doubts it's very easy.
Thank you. Thank you.
It's not very easy. Is it very difficult? I don't know. For me, it is.
More questions? I have one at the very beginning. You said Georgi had provided a very short proof of Wigner's, the non-bijective versions of Wigner's theorem, right? The physics letters or something like that. Yeah. So does that argument also then go ahead to prove Wigner's theorem itself? In the bijective, if you add a bijective assumption, then can this proof be refined to prove Wigner's theorem as well?
No, of course because I mean here Georgi proved this without bijectivity assumption. Then if you add bijectivity, then of course this U has to be bijective, so it is actually unitary or anti-unitary. Wigner's theorem is of course trivial consequence. But the question, now I understood your question in a different way. If you add bijectivity assumption, can this proof be made even shorter? And that's something that I cannot answer it. Maybe that's interesting question, yeah. So I mean, Geger, but his proof of this statement is so short, but maybe it can be made even shorter if you add here bijectivity assumption, yeah. Because those questions, here those questions these are typical questions that we mathematicians ask. We have Wigner's theorem is beautiful theorem, is simple, and it's very important. And then, of course, in mathematics, we ask, can we do better? I doubt that in physics they are really interested in. But actually, when I published this paper, maybe it's not true, because I got a letter from a mathematical physicist, and he found this result very interesting, and he said that this sending cost per cost and all those things, that this is for him important. Now, of course, theoretical physics is as theoretical as pure mathematics. Because nothing, theoretical physics is closer to mathematics than to physics.
Yeah, very good. Yeah, that was my second question, is whether that approach can be used to do any more refinements as well after Wigner's theorem. But yeah, Georgi's approach. Yeah. Okay, further questions? Okay, I guess if there are no further questions. Yeah, go ahead.
Hello, Apurva.
Yeah, we can hear you. Go ahead, Professor Singh. Yeah.
Yeah, you see, maybe for young people, we should emphasize that the maximum size of any mutually orthogonal system of projections is the dimension of the space. And otherwise, we look for few angles. Like in mutually unbiased basis, we look only when the inner products are mod of that is 1 by root d, where d is the dimension. And then there are more results on a few angles, and there is a lot of literature on that. And also there is a lot of literature on equiangular lines. That means projections for which the inner products are just, modulus of inner product is just the same. So it is equiangular lines.
Yeah. Yeah, I believe these are all so basic and natural questions that, I mean, people are doing. Of course, this COSP. This is just, it corresponds to orthonormal basis. Not exactly, because a projection of rank 1 is not. Projections of rank 1 are not in bijective correspondence with unit vectors. They're in bijective correspondence to unit vectors up to the face factor. I mean, if you multiply a unit vector by, say, by I, or by any complex number of modulus 1, you get the same projection of rank 1 but different vectors. But anyway, so it's a lot of literature. It's from different point of view. Projections of rank 1, then there are bases and orthonormal bases, and then there are frames, and these are all such important basic things that there is a lot of literature. There is a lot of literature on principal angles. When you have, instead of projections of rank 1, you have projections of rank 2 or projections of rank 3 and so on. There is a mutual position of two projections of rank 5. You have the famous, what is that? Halmos two projections theorem, and so on and so on and so on. There are plenty of things here around. Thank you.
Thank you. Wonderful talk.
Thank you.
Some questions? Okay, if not, then let's thank the speaker again for very, very clear and lovely.
Thank you very much for your attention. And thank you for the invitation, and I'm greetings from cold winter. I am envy. You are in a pleasant climate right now. Well, okay.